something just changed. After disappearing behind the sun, 3I Atlas has re-emerged, and what astronomers are seeing now is raising more questions than answers. The first images from Lowell Observatory captured on Halloween show a comet that shouldn't exist according to everything we know about interstellar visitors. While Earth anxiously waited for any sign of this cosmic traveler, telescopes at the Discovery Telescope in Arizona locked onto a faint smudge rising above the northeastern horizon. After 8 days of solar conjunction, when the comet was completely hidden from our view, 3I Atlas is back. But it's what scientists discovered during their analysis that's keeping them up at night. The surface of this interstellar wanderer is covered with something unprecedented. A 15 to 20 meter thick crust of organic compounds, forged not in its home star system, but during billions of years drifting through the galaxy. Imagine that. Everything we're observing, every measurement we're taking, isn't showing us the pristine material from another solar system. We're looking at a shell, transformed by cosmic radiation during a journey that began before our solar system even formed. Belgian and American researchers ran the numbers through computer simulations. What they found rewrites our understanding of interstellar objects. Galactic cosmic rays, particles accelerated by supernovae and colliding black holes, have been bombarding this comet for 3 to 11 billion years. These high-energy particles penetrated deep into its surface, breaking apart molecules, creating complex carbon chains, then destroying them again. It's a cosmic forge, running continuously for eons. Here's where it gets strange. The composition analysis shows something that doesn't match any comet we've ever studied. Carbon dioxide dominates the emissions, 7.6 times more abundant than water. Comets are supposed to be dirty snowballs, primarily water ice. This one barely qualifies. The spectral signature reveals elevated carbon monoxide and an unusually red reflection spectrum from organic molecules coating the surface. But wait, there's more that doesn't add up. The nickel to iron ratio in the gas plume matches industrial alloys, not natural cosmic dust. The nickel to cyanide ratio is orders of magnitude higher than every known comet, including 2I Borisov, our previous interstellar visitor. Some researchers are putting the probability of these characteristics occurring naturally at less than 1%. The polarization measurements are off the charts. Extreme negative polarization, unprecedented for any comet ever observed. Not just unusual, statistically anomalous when compared to the entire catalog of cometary data. When light bounces off the dust and gas around 3I Atlas, it behaves in ways that conventional models can't explain. Then there's the trajectory, a retrograde orbit aligned within 5 degrees of the ecliptic plane, threading through the solar system like it was planned. The statistical likelihood? 0.2%. It passed within tens of millions of kilometers of Mars, Venus, and Jupiter, arriving at perihelion when Earth couldn't observe it directly. The confluence of these orbital coincidences has a combined probability of 0.005%. During July and August, observers documented something that challenged basic physics. A sunward jet, an anti-tail pointing directly toward the sun. Not an optical illusion created by perspective like familiar comets display. An actual jet of material shooting in the wrong direction. The papers are published, the data is solid, but the mechanism remains unexplained. As 3I Atlas approached perihelion on October 29th, space-based solar observatories captured rapid brightening beyond any known comet behavior. The object became bluer than the sun itself. Think about that. A ball of ice and dust, outshining our star in certain wavelengths. Stereo, SOHO, and GOES 19 all recorded the same phenomenon. Now here's something that makes theoretical physicists excited. The close passage near the sun created a perfect natural laboratory for testing Einstein's general relativity. Gravitational lensing calculations show the sun's gravity should deflect light from 3I Atlas by 0.27 arcseconds per degree of angular separation, it's measurable. The Atacama Large Millimeter Array detected the comet 4 arcseconds away from its predicted position near perihelion. Some of that deviation could be gravitational lensing, but there's another explanation floating around, one that's harder to accept. Non-gravitational acceleration. The comet changed velocity without any obvious gravitational cause. If it's outgassing, if jets of sublimating ice are pushing it around like a natural rocket, then it should have lost at least 15% of its mass. That's over 5 billion tons of gas and debris. A massive cloud that should be impossible to miss. Observations continuing through November and December will either confirm this cloud exists, or we'll have a 10th anomaly to explain. Amateur astronomers across the Northern Hemisphere can now observe 3I Atlas with standard telescopes. Just a smudge above the eastern horizon during morning twilight, but an increasingly visible smudge. As the comet moves northward and gains separation from the sun, larger observatories around the world are beginning their observation campaigns. The window for spectroscopic analysis is now wide open. The organic crust theory solves some mysteries while creating others. If radiation processing altered the surface to a depth of 20 meters over billions of years, then the comet has lost less than 1 meter of material during most of its passage through the solar system. The intense heating near perihelion might have sublimated a few dozen more meters, but only under specific size conditions. Either way, we're not seeing primordial material from another star system. We're analyzing the radiation-processed remnants, which brings us to an uncomfortable question. How do we study the origin of an interstellar object when its surface has been fundamentally transformed? The spectral signatures, the gas emissions, the dust composition, all of it might tell us more about galactic radiation effects than about the comet's birthplace. It's like trying to read a book that's been left out in the sun for 3 billion years. The words are still there, but they're not the original text. Some researchers are proposing alternative interpretations. What if the anomalies aren't separate coincidences? What if they're connected by something we haven't considered? The alignment with the famous wow signal direction, within 9 degrees, probably means nothing. Probably. The trajectory optimization for planetary flybys while avoiding easy Earth observation. Statistical outlier, but not impossible. The industrial metal ratios. The unusual polarization. The unprecedented brightening. Each one individually explainable if you really want to explain it. But together, 9 confirmed anomalies. Possibly 10 depending on what the next observations reveal. At some point, you run out of statistical wiggle room. Nature is weird. The universe is vast, and unlikely things happen. But do they all happen to the same object? The scientific community is watching December 19th with particular attention. That's when 3I Atlas makes its closest approach to Earth. Not close enough to threaten us, but close enough for unprecedented observational opportunities. Every major telescope that can point at it will be collecting data. Spectroscopy, photometry, polarimetry, radar if we're lucky. This is our chance to gather evidence that might not come again for decades or longer. The post-perihelion observations are revealing details that pre-perihelion data couldn't capture. As the comet heats up and moves away from the sun, volatile compounds sublimate from deeper layers. Each gas molecule that escapes carries information about composition, temperature, and internal structure. The spectrographs are working overtime, breaking down the light into component wavelengths, searching for molecular fingerprints. Qicheng Zhang from Lowell Observatory demonstrated something remarkable. Using a 6-inch amateur telescope, he captured 3I Atlas when it was just 16 degrees from the sun, 5 degrees above the horizon. The comet was visible during morning twilight, that narrow window when it's above the horizon, but the sun hasn't brightened the sky too much. If a small telescope can see it under these conditions, the data harvest from professional instruments will be extraordinary. The organic crust discovery changes everything about how we interpret interstellar objects. When galactic cosmic rays slam into ice and carbon compounds, They trigger a cascade of chemical reactions. Carbon monoxide transforms into carbon dioxide. Water molecules break apart in a process called radiolysis. Complex organic molecules form, then shatter, then reform in different configurations. It's continuous chemical evolution, powered by the most energetic particles in the galaxy. Think about the implications. Every interstellar object we detect might be wearing a mask of radiation-processed material. The surfaces we analyze, the spectra we measure, they're telling us about the journey through space, not necessarily about the origin. It's like trying to determine what type of tree a piece of driftwood came from after it spent centuries in the ocean. The original information is still there, buried under layers of transformation. But here's what keeps astronomers up at night. The math doesn't quite work for a purely natural explanation of all the observations together. Take the trajectory alone. Flying retrograde, nearly aligned with the ecliptic, arriving precisely when multiple planets are in range while Earth has no direct line of sight. Program that into an orbital mechanics simulator and watch the probability numbers drop into statistical noise. Add the composition anomalies, industrial-grade nickel ratios, minimal water for a supposed comet, extreme polarization that breaks known models. Each one stretches credibility. Stack them together, and you're either witnessing the cosmic equivalent of winning the lottery 9 times in a row, or something else is happening. The radiation processing theory explains the organic crust. It explains the carbon dioxide dominance. It explains the red spectral signature. But it doesn't explain the nickel enrichment. It doesn't explain the trajectory. It doesn't explain the anti-tail dynamics. And it certainly doesn't explain why the comet brightened beyond known limits and turned bluer than the sun at perihelion. Solar observatories caught something during those crucial hours when 3i Atlas was closest to the sun. The brightness curve spiked harder and faster than any comet on record. Not just a little unusual, but completely outside the normal distribution. And the color shift, that blue tint, suggests something about the energy distribution that standard sublimation models don't predict. Some scientists are starting to whisper about what they're not saying publicly. The data is solid, the observations are repeatable, the anomalies are documented, but the conclusions that logically follow from the data lead to uncomfortable places. Academic careers get built on careful, conservative interpretations. Going public with speculative ideas invites ridicule and professional consequences. So the conversations happen in private, in emails marked confidential, in late-night discussions after conferences. What if we're looking at this backwards? What if the question isn't whether these anomalies can be explained naturally, but whether we're brave enough to consider alternatives when the natural explanations require increasingly elaborate special pleading? Science advances when someone looks at impossible data and says, maybe our assumptions are wrong. The timing is almost theatrical. Discovered in July, peak visibility in August and September, disappearing behind the sun in October, re-emerging in November, with December's closest approach still ahead. Like a cosmic magician's reveal, each act showing something new, building toward a finale that we can't quite predict. Radio telescopes maintained observations throughout the perihelion passage. While optical telescopes lost sight of 3i Atlas against the sun's glare, radio wavelengths penetrated through. The data from ALMA showing that 4 arcsecond position deviation is particularly interesting. Yes, gravitational lensing accounts for a fraction of that displacement, but only a fraction. The rest suggests acceleration without an obvious mechanism. If it's outgassing, show us the cloud. 5 billion tons of ejected material doesn't just disappear. It reflects sunlight. It scatters radiation. It leaves a spectroscopic signature kilometers wide. The upcoming observations through November and December will either reveal this massive debris field or confirm its absence. Either answer is significant. Find the cloud, and we validate natural comet behavior with extreme parameters. Don't find the cloud, and we need a new category of explanations. The amateur astronomy community is mobilizing. Clear skies and low eastern horizons are the requirements. Charts showing the comet's position relative to background stars are circulating through observation networks. People are waking up before dawn, setting up telescopes in dark fields, hoping to capture their own photons from an object born around another star billions of years ago. That connection, that direct link between backyard telescope and interstellar traveler, it's profound. Professional observers are coordinating multi-wavelength campaigns. Optical telescopes tracking position and brightness. Infrared instruments measuring thermal emission and dust properties. Radio arrays analyzing molecular outgassing and magnetic fields. Ultraviolet satellites checking for hydrogen and oxygen signatures. X-ray detectors looking for unexpected high-energy emissions. Every available sensor pointing at this cosmic anomaly. The gravitational lensing experiment is particularly elegant. Einstein's general relativity predicts exactly how much the sun's mass should bend spacetime, and therefore how much it should deflect light passing nearby. The math gives 0.27 arc-seconds per degree of angular separation. That's measurable with modern instruments. If the ALMA data contains evidence of this gravitational deflection mixed in with the unexplained positional deviation, it would be a beautiful confirmation of relativity using an interstellar object as the test source. Universities are rushing to allocate telescope time. Graduate students are writing proposals. Postdocs are analyzing data in real time. This is what astronomy looks like when something genuinely unexpected shows up. The careful, methodical pace of research suddenly accelerates. Papers get written in weeks instead of months. Preprints appear daily on Arxiv. Conference calls happen across time zones. The community mobilizes because opportunities like this are rare. Meanwhile, the theoretical models are struggling to keep up. You can't just tweak a parameter here and there to make all 9 anomalies fit within standard comet physics. The models that explain the organic crust don't address the trajectory. The dynamics that account for the anti-tail don't predict the brightness surge. The composition that matches the spectroscopy doesn't explain the polarization. It's like trying to solve a Rubik's Cube, where fixing one face scrambles 3 others. Some researchers are taking a step back and asking fundamental questions. What are the priors? What assumptions are we bringing to this analysis? We've studied exactly 3 confirmed interstellar objects, Oumuamua, Borisov, and now 3I Atlas. That's not a statistically significant sample. We don't actually know what's normal for objects from other star systems. Maybe extreme variability is the norm, and we've been unlucky to catch the weird ones. Or maybe we've been extremely lucky. The WOW signal correlation probably means nothing. Radio astronomy has documented thousands of unexplained signals over the decades. One of them is bound to align with something interesting by pure chance. But there it is in the data, 9 degrees of separation between the origin point of the most famous CD detection and the arrival trajectory of the most anomalous interstellar object ever observed. Coincidence wears thin when it happens repeatedly. Here's what we know for certain. 3I Atlas is real, it's interstellar, and it's displaying behaviors that push the boundaries of established comet science. The question isn't whether the data is accurate. Multiple independent observatories using different instruments and techniques have confirmed the measurements. The question is what framework we use to interpret that data. Consider the mass and velocity combination. The nucleus is roughly 1,000,000 times more massive than Oumuamua and 1,000 times heavier than Borisov, while moving faster than both. Calculate the probability of detecting an object with these specific parameters, and you get numbers below 0.1%. Add that to the list of statistical outliers. The size estimates range from 220 meters to 2.8 kilometers in radius. That's a huge uncertainty range, but even the lower bound represents a substantial object. If it's on the smaller end, and the organic crust is 20 meters thick, then a significant fraction of the radius is radiation-processed material. Peel back that crust, and what's underneath? Original cometary ice from another star system, or something else entirely? The water content is the smoking gun for many researchers. 4% water by mass. Comets from our solar system are typically 60 to 80% water ice. Even accounting for billions of years of radiation processing, the discrepancy is hard to explain. Where did all the water go? Sublimated away during the interstellar journey? Transformed into other compounds? Or was it never there in the first place? Some planetary scientists are proposing that 3I Atlas might not have formed in a typical stellar system. What if it's a fragment from the mysterious frontier of the early Milky Way? A chunk of material from when the galaxy was young, and chemistry was different. The carbon and organic-rich composition could reflect primordial conditions that no longer exist in modern star-forming regions. It's an elegant hypothesis that explains the unusual chemistry while keeping everything natural. But the trajectory keeps coming back to haunt every natural explanation. Orbital mechanics is precise mathematics. You can't hand-wave away the alignment with the ecliptic plane. You can't dismiss the planetary flyby geometry as random chance when the numbers say otherwise. And you definitely can't ignore the fact that it reached perihelion during the optimal window to avoid Earth-based optical observation. The brightening behavior near perihelion deserves its own investigation. Standard comet physics predicts gradual brightening as volatile ices sublimate with increasing solar heating. What stereo, SOHO, and GOES observed was anything but gradual. The light curve showed rapid, almost exponential brightening over a period of hours. Then, the color shifted blue, indicating a change in the emission spectrum that doesn't match thermal radiation from heated dust. Energy doesn't appear from nowhere. If 3I Atlas suddenly became brighter and bluer, something was releasing stored energy or converting energy from one form to another. Conventional explanations involve sudden exposure of fresh ice or catastrophic fragmentation. Both scenarios should produce observable debris and extended coma. The observations through November will show whether that debris exists. The organic crust composition raises another question. 15 to 20 meters of carbon-rich compounds processed by cosmic rays for billions of years. That's not just a thin coating, it's a substantial shield. How does sublimation occur through such a barrier? The usual model involves solar heating, creating pressure that cracks the surface, allowing gases to escape. But that process should expose fresh material continuously. The fact that we still see processed organics suggests either the crust is regenerating or the sublimation mechanism is different from what we think. Think about the thermal properties. Organic compounds are excellent insulators. A 20-meter thick crust would block most solar heating from reaching interior ice. Yet 3I Atlas shows strong outgassing activity. Either the crust has channels and fractures allowing heat penetration, or energy is reaching the interior through non-radiative means. Each explanation leads to different predictions about what we should observe. The anti-tail phenomenon from July and August remains unexplained. Jets of gas and dust typically flow away from the sun due to radiation pressure and solar wind. A sunward jet requires either unusual dust properties that make particles gravitationally fall toward the sun faster than radiation pushes them away, or active propulsion from venting on the sunward side. Neither explanation fully accounts for the observed jet morphology. Several research teams are now looking at the possibility of subsurface activity. If the interior contains pockets of volatile ices under pressure, sudden releases could create jets in any direction regardless of solar heating. It's similar to geysers on Earth, or the nitrogen plumes on Pluto. This would explain directional jets, but it requires specific internal structure and composition. The polarization data is particularly troublesome for standard models. Light, interacting with dust particles, produces predictable polarization patterns based on particle size, shape, and composition. The extreme negative polarization from 3I Atlas suggests dust properties unlike any other observed comet. Either the radiation processing created uniquely structured particles, or the dust isn't ordinary silicate and carbon grains. Laboratory experiments are trying to reproduce the conditions. Teams are exposing various ice and organic mixtures to simulated cosmic ray bombardment, then analyzing the resulting materials. If they can create dust with the observed polarization properties, it would support the natural processing hypothesis. If not, we need alternative explanations for what's coating this comet. The nickel enrichment continues to puzzle geochemists. Natural cosmic dust does contain nickel, but the ratio to iron typically reflects solar system averages. Industrial alloys are engineered to have specific nickel-to-iron ratios optimized for strength and corrosion resistance. The fact that 3I Atlas emissions show ratios matching industrial specifications rather than natural abundances is statistically weird. Not impossible, but requiring special formation conditions. Could a supernova create unusual elemental ratios? Absolutely. Different layers of an exploding star synthesize different elements. Material ejected from specific zones might have non-standard compositions. If 3I Atlas formed from supernova ejecta rather than a normal protoplanetary disk, that could explain the chemistry. It's testable too. Other elements should show corresponding anomalies if this is the right explanation. The December 19th close approach will provide the highest resolution data we've had yet. Distance of roughly 0.4 astronomical units, close enough for radar observations if the geometry works out. Radar can penetrate dust and gas to map the actual nucleus shape and size. It can detect rotation rates and surface features. Most importantly, it can measure the radar reflectivity, which reveals composition and structure. If 3I Atlas is a natural comet, even an extremely unusual one, the radar signature should show irregular shape with varied surface properties. That's what happens when a dirty snowball forms through accretion and ages through space weathering. If the radar shows something else, something with unexpected uniformity or geometric regularity, that would be significant. Ground-based telescopes are planning spectroscopic campaigns spanning multiple nights. Watch how the emission lines change over time. Monitor the production rates of different molecules. Look for correlations between gas release and solar distance or rotation phase. Build up a complete picture of the comet's activity cycle. The data from these campaigns will fill in gaps and test competing models. Space-based ultraviolet observatories are particularly important. The Lyman alpha emission from hydrogen atoms around comets traces water dissociation. If 3I Atlas has as little water as the initial measurements suggest, the hydrogen cloud should be much smaller than typical comets, confirming that would validate the compositional anomaly and rule out observational artifacts. One hypothesis that keeps resurfacing in private discussions is that we might be looking at a fragment rather than an intact primordial object. What if 3I Atlas was once part of something larger that broke apart? The organic crust would have formed on the original body, then been inherited by the fragment. The unusual composition could reflect interior materials exposed by the breakup event. It's a middle ground explanation that accounts for some anomalies while remaining within natural processes. But fragmentation events usually leave evidence. Debris trails, companion fragments, irregular shapes from the break. Observations so far haven't revealed obvious fragmentation signatures. The light curve shows stable brightness without sudden variations that would indicate an unstable or fragmenting object. Of course, if the breakup happened millions of years ago during the interstellar journey, the other fragments are long gone and undetectable. The age question is fascinating on its own. If 3I Atlas really did spend 3 to 11 billion years traveling between stars, It predates most of the planets in our solar system. It was already ancient when Earth formed. The organic molecules coating its surface are older than life itself. We're analyzing chemistry that existed before biology, before anything we'd recognize as familiar planetary conditions. What was the galaxy like when this object began its journey? The Milky Way had different structure, different stellar populations, different chemical abundances. Star formation rates were higher. Supernova frequencies were different. The interstellar medium had different properties. If 3I Atlas formed during that era and carries information about those conditions, it's a direct sample of ancient galactic history. But there's a contradiction in that picture. Objects wandering through interstellar space for billions of years should accumulate impacts from micrometeoroids and dust. Each collision erodes the surface, creates craters, changes the composition. The radiation processing would smooth out some of these features, but not all of them. Detailed radar or close-up imaging should reveal impact scars if this object really is billions of years old. The rotation rate will tell us something too. Natural objects tumbling through space for eons should have complex rotation states from accumulated torques and impacts. Measure the light curve over enough time and you can determine if it's rotating simply around one axis or tumbling chaotically. Simple rotation might suggest a recent formation or a recent event that stabilized the spin. Complex tumbling would fit the ancient wanderer narrative better. There's another aspect that nobody wants to discuss openly, but everyone is thinking about: the detection rate of interstellar objects. We found Oumuamua in 2017, Borisov in 2019, and now 3I Atlas in 2025. 3 objects in 8 years. Statistical models predicted we'd detect maybe 1 per decade with current survey capabilities. We're seeing triple the expected rate. Either the galaxy contains far more interstellar objects than models predicted, or we're getting unusually lucky with discoveries, or something about our recent detections is non-random. The first explanation requires reworking population models. The second is statistically possible, but increasingly unlikely with each new detection. The third explanation leads to uncomfortable speculations about selection effects or targeting. Consider this scenario. If an advanced civilization wanted to survey solar systems, sending physical probes makes sense. They'd be designed to survive interstellar transit, which means radiation shielding and durable construction. They'd need propulsion for course corrections, which creates non-gravitational acceleration. They'd optimize trajectories for planetary flybys to maximize data collection. And they'd probably arrive when detection is difficult to avoid immediate attention. Now look at the characteristics of our 3 interstellar visitors through that lens. Oumuamua tumbling, elongated, with unexplained acceleration that didn't match comet outgassing. Borisov more conventional, possibly a control sample or comparison case. 3I Atlas combining extreme anomalies with optimal trajectory timing. Each one teaching us something different about what's possible. This is where the conversation gets dangerous for careers. Suggesting the possibility of artificial origin invites immediate criticism. The data doesn't definitively prove it, so why even mention it? But the data doesn't definitively prove natural origin either. At some point, when enough anomalies accumulate, refusing to consider all possibilities becomes unscientific. The academic community has protocols for discussing sensitive topics. You present the natural explanations first. You emphasize the uncertainties. You use phrases like requires further investigation and remains unexplained by current models. You don't jump to exotic conclusions, but behind the careful language, there's an awareness that something genuinely strange is happening. Public communication about 3I Atlas faces challenges too. How do you convey the significance without creating panic or false expectations? The object isn't dangerous. It's not going to hit Earth. It's not definitively artificial. But it is genuinely anomalous in multiple ways that strain conventional explanations. Finding the right balance between honesty and responsibility is tricky. Some researchers argue we should simply present the observations and let people draw their own conclusions. Release all the data, publish all the measurements, show the statistical analyses, and trust the public to understand nuance and uncertainty. Others worry that incomplete information gets misinterpreted, that selective reading of data leads to unfounded conclusions, that sensationalism drowns out careful science. The media coverage so far has ranged from sober scientific reporting to wild speculation. Some outlets focus on the radiation crust discovery and what it teaches us about galactic chemistry. Others lead with the alien spacecraft angle and bury the uncertainties deep in the article. The scientists caught in the middle try to correct misrepresentations while acknowledging legitimate mysteries. Meanwhile, the observations continue. Every night that weather permits, telescopes track this wanderer. Every spectrum adds data. Every image refines position measurements. Every detection in a new wavelength constrains models. The dataset is growing exponentially compared to what we had for Oumuamua or even Borisov. Whatever 3i Atlas turns out to be, we're studying it more thoroughly than any previous interstellar object. The November observations are particularly crucial. This is the window when the comet is far enough from the sun for good visibility, but close enough to Earth for strong signal. Atmospheric conditions matter too. Clear, stable nights produce the best spectra. Turbulence blurs images and adds noise. Observatories at high altitude with good seeing conditions are prioritized for the most detailed measurements. International collaboration is essential. The comet is visible from northern latitudes primarily, but different longitudes provide different observation windows. As Earth rotates, one observatory sets and another rises, maintaining continuous coverage. Coordinating observations across continents means scheduling challenges and data sharing agreements, but the payoff is comprehensive monitoring. Amateur contributions are proving valuable too. A global network of small telescopes can provide temporal coverage that no single facility can match. While they can't match the sensitivity or resolution of professional instruments, they can track brightness changes, detect outbursts, and provide early warnings for targeted follow-up. It's citizen science at its finest, amateur and professional working together. The December close approach is being planned like a military campaign. Target acquisition windows are calculated. Instrument configurations are optimized. Observation schedules are drafted and revised. Backup plans account for weather, technical issues, and unexpected developments. This is humanity's best shot at understanding 3i Atlas before it leaves the inner solar system forever. After December, the comet continues outbound. By mid-2026, it will be beyond Jupiter's orbit, fading from view of all but the largest telescopes. Eventually, it disappears back into the interstellar void, carrying its secrets with it. Whether we've solved the mysteries by then or added more questions to the list remains to be seen. The legacy of 3i Atlas will persist regardless. It's forcing astrophysics to confront assumptions about interstellar objects, about cometary behavior, about what's possible in natural systems. The organic radiation crust discovery alone will reshape how we interpret future detections. The trajectory statistics will inform search strategies. The compositional anomalies will guide laboratory experiments. And there's the possibility, slim but non-zero, that we're witnessing something unprecedented. That 3i Atlas represents our first confirmed detection of technology from beyond Earth. That the anomalies aren't coincidences or measurement errors or exotic natural phenomena, but signatures of purpose and design. If that's true, everything changes. Consider what it would mean. Confirmation that we're not alone. Proof that interstellar travel is achievable. Evidence that other civilizations exist and are actively exploring. The philosophical implications alone would be staggering. Religions would grapple with non-human intelligence. Governments would reassess cosmic priorities. Science would pivot toward understanding the visitors. But we're not there yet. The data is ambiguous. Natural explanations remain possible even if increasingly contrived. Extraordinary claims require extraordinary evidence, and while the evidence is certainly unusual, it hasn't crossed the threshold to extraordinary. More observations, more analysis, more testing of alternative hypotheses. That's the path forward. What we can say with confidence is that 3I Atlas has earned its place in history. Third, confirmed interstellar object. Most thoroughly observed visitor from another star system. Source of multiple discoveries about radiation processing and galactic chemistry. Catalyst for debates about scientific methodology and the search for intelligence. Object of fascination for millions watching from Earth. The story isn't over. November and December observations will add chapters. Analysis of that data will continue through 2026 and beyond. Papers will be written, debated, revised. Models will be tested, refined, or discarded. The scientific process moves forward, accumulating knowledge even when definitive answers remain elusive. For now, 3I Atlas moves through our solar system, a traveler from distant reaches carrying mysteries we're only beginning to understand. Every photon it reflects tells part of the story. Every molecule it releases adds to the narrative. Every measurement brings us closer to truth, whatever that truth turns out to be. And we watch, we measure, we wonder, and we wait to see what revelations December brings. The human response to 3I Atlas reveals something about ourselves too. When confronted with genuine cosmic mystery, we react in predictable ways. Some embrace the uncertainty, finding beauty in unanswered questions. Others demand immediate explanations, uncomfortable with ambiguity. Scientists occupy the middle ground, professionally obligated to maintain skepticism while personally drawn to the extraordinary possibilities. Social media exploded with speculation when the first anomalies were reported. Hashtags trended. Memes proliferated. Amateur detectives pored over every released image, searching for hidden details that professional astronomers might have missed. The democratization of information means everyone can participate in the discovery process, for better or worse. Crowdsourced analysis has occasionally caught legitimate anomalies, but it's also generated countless false alarms. The psychological impact of potential first contact, even indirect contact through an uncrewed probe, shouldn't be underestimated. Surveys show that most people believe intelligent life exists elsewhere in the universe, but belief and confirmation are different experiences. Actually finding evidence transforms abstract philosophy into concrete reality. It forces confrontation with humanity's place in the cosmos. Religious institutions are already preparing responses. Some theological frameworks easily accommodate extraterrestrial intelligence. Others require significant reinterpretation of core texts and doctrines. The discovery wouldn't necessarily shake faith, but it would certainly reshape how that faith is understood and expressed. The universe is bigger and stranger than ancient prophets imagined. Government agencies are watching too, though they're saying little publicly. Space agencies have protocols for unexpected discoveries. Military organizations track all objects near Earth, natural or otherwise. Intelligence services monitor for technological signatures. If 3I Atlas turned out to be artificial, the geopolitical implications would be profound. Who speaks for Earth? Who decides how to respond? Who controls the narrative? These questions have theoretical answers in international treaties and UN committees, but theory meets reality awkwardly. When seconds count for communication decisions, when media cycles demand immediate reactions, when public pressure builds for transparency, the carefully constructed protocols might not hold up. The institutional response to genuine first contact would likely be messy, contradictory, and politically fraught. Science fiction has prepared us poorly for actual contact. Stories feature dramatic encounters, clear communication, obvious intentions. The reality of 3i Atlas, if it is artificial, is far more ambiguous. An object passing through, showing no interest in slowing down or establishing contact, leaving us to puzzle over indirect evidence and statistical anomalies. No dramatic reveal, no cosmic greeting, just questions piling on questions. Maybe that's the point, though. An advanced civilization conducting surveys wouldn't necessarily want to disrupt the societies they're studying. Minimal interference, collect data, move on. The prime directive from Star Trek was fiction, but it reflected reasonable speculation about how responsible exploration might work. If 3i Atlas is a probe, its handlers might be watching our reaction, noting how we respond to ambiguity. Or maybe we're pattern-seeking primates, finding meaningful shapes in random noise. Humans are exceptionally good at detecting patterns, even when no patterns exist. It's a survival trait that served our ancestors well. Better to see a predator that isn't there than miss one that is. But that same trait leads to conspiracy theories, false correlations, and seeing intelligence where only nature operates. The scientific method exists partly to counter our pattern-seeking biases, demand reproducible evidence, test alternative hypotheses, quantify uncertainties, don't accept extraordinary claims without extraordinary proof. These standards protect us from fooling ourselves, but they also create tension when genuinely extraordinary phenomena occur. How much evidence is enough? When does skepticism become denial? Different researchers have different thresholds. Some see the 3i Atlas anomalies and think we've crossed into genuinely unprecedented territory, requiring new explanations. Others see the same data and think we need better natural models, more observations, more patience before jumping to exotic conclusions. Both positions are defensible. Both come from qualified experts analyzing the same information. This intellectual diversity is actually healthy for science. Consensus emerges from debate, not uniformity. If everyone agreed immediately, it would suggest groupthink rather than careful analysis. The disagreement over 3i Atlas interpretations reflects genuine scientific uncertainty, not failure of method. We're supposed to argue about ambiguous data. That's how knowledge advances. The media often presents scientific debates as if one side must be right and the other wrong. Reality is messier. Multiple explanations can be partially correct. The truth often involves elements from competing hypotheses. 3i Atlas might be a natural comet with unusual formation history, creating some anomalies, while other anomalies reflect observational biases we haven't fully accounted for. Or it might be something we haven't imagined yet. Public understanding of scientific uncertainty is improving, but still problematic. People want definitive answers. Scientists offer probabilities and confidence intervals. That disconnect creates frustration on both sides. Researchers feel misunderstood when their careful caveats get stripped away in headlines. The public feels misled when scientific consensus shifts as new data arrives. Building trust requires better communication in both directions. Educational outreach around 3i Atlas has been extensive. Astronomers are hosting public viewing sessions. Museums are creating exhibits. Planetariums are running special programs. YouTube channels are exploding with explanatory content. The goal is helping people understand not just what we're observing, but how we observe, how we analyze, how we reach conclusions. Science literacy matters more than any single discovery. The economic implications are subtle but real. Private space companies are watching closely. If interstellar objects are more common than expected, or if they're artificial, that changes business models for space exploration. Detection networks become more valuable. Intercept missions become feasible. The entire strategic landscape of space commercialization shifts. Investment decisions today depend on assumptions about what's out there. Academic funding is already responding. Grant proposals mentioning interstellar objects get extra attention. Universities are creating new research positions. Instruments designed for exoplanet hunting are being repurposed for object detection. The field is growing, driven by the prospect that we might actually encounter visiting objects with some regularity. If we caught 3 in 8 years, more are surely coming. That projection assumes random arrivals. If the detection rate isn't random, if there's clustering or intentional targeting, then the entire statistical framework breaks down. We'd be dealing with a fundamentally different situation. The search for extraterrestrial intelligence would shift from passive listening to active analysis of physical artifacts passing through our neighborhood. SETI has traditionally focused on radio signals. The assumptions were that radio is universal, that civilizations broadcast, either intentionally or as technological leakage, that we might catch those transmissions. But physical probes have advantages. They can carry far more information than any broadcast. They can make detailed local observations. They can potentially interact with what they find. If you're serious about exploration, you send hardware. The Voyager probes carry golden records with information about humanity. We sent messages in physical form because we understood their permanence and richness. An advanced civilization would presumably reach the same conclusion. Send probes to interesting star systems. Gather data. Maybe leave markers. Over millions of years, a single civilization could survey a significant fraction of the galaxy. That's speculation, of course. We don't know how common technological civilizations are. We don't know if they survive long enough to conduct galactic surveys. We don't know if interstellar travel is practical even for advanced societies. The Drake equation has too many unknown variables. But 3 interstellar objects in 8 years, with one showing multiple anomalies, shifts the probability landscape. Fermi's paradox asks where everyone is. If civilizations are common, if interstellar travel is possible, we should see evidence everywhere. The silence has been deafening. But maybe we weren't looking in the right way. Maybe the evidence isn't radio signals, but objects moving through our solar system, distinguishable from natural bodies only through careful statistical analysis of multiple parameters. The philosophical questions spiral outward. If intelligence is common, why the variety of approaches? Oumuamua accelerated, but stayed silent. Borisov looked completely natural. 3i Atlas shows intermediate characteristics. Different missions from different civilizations, different technologies from the same source, or natural objects plus 1 or 2 artificial ones, creating a confusing mixed sample. We won't solve these questions in November or December. We might not solve them in our lifetimes, but every observation adds data. Every measurement constrains possibilities. Every analysis refines our understanding. The process is gradual, frustrating, exciting, and utterly human. We're doing what our species does best, looking at the unknown and trying to make sense of it. The children growing up watching this story unfold will inherit a different universe than previous generations knew. Whether 3i Atlas proves natural or artificial, whether we find more interstellar visitors, or this proves a statistical fluke, the awareness has shifted. We're not alone in space. Objects from other star systems reach us. The galaxy is dynamic, interconnected, accessible. That changes everything about how we think about our future. Space exploration advocates argue that staying confined to one planet is existential risk. Interstellar objects demonstrating regular visitation strengthen that argument. If the galaxy is crowded with wandering bodies, if some might be artificial, if civilizations really do explore beyond their home systems, then humanity needs to develop similar capabilities. Not from fear or competition, but from recognition that this is what technological species do. The engineering challenges remain immense. Even reaching nearby stars requires revolutionary propulsion technology. Surviving interstellar transit demands solutions we haven't invented yet, but watching 3i Atlas cross our solar system proves it's possible. Something made that journey. Whether natural process or designed artifact, the physics allows it. What nature or others have done, we might eventually do too. That's the ultimate legacy of 3i Atlas, regardless of what it turns out to be. Proof that interstellar space is crossable. Demonstration that our solar system receives visitors from cosmic distances. Inspiration to imagine humanity's future among the stars. And reminder that the universe is stranger, richer, and more surprising than we typically assume. December 19th approaches. Telescopes are ready. Observers are scheduled. The world watches and wonders. Whatever data emerges, whatever analyses follow, whatever conclusions eventually form, this moment matters. We're witnessing something rare and possibly unique. An object from another star system, displaying behaviors we struggle to explain, offering mysteries we're only beginning to unravel. The questions outnumber answers. The uncertainties outnumber certainties. The unknowns dwarf the knowns. That's how it should be. That's how discovery works. Comfortable certainty means we've stopped learning. Uncomfortable ambiguity means we're at the frontier, pushing into territory nobody has mapped before. 3i Atlas brought us to that frontier. Where we go from here depends on what we find next, and whether we're brave enough to follow the evidence wherever it leads.